Today is lecture 23. We'll just do one lecture today. Like I mentioned a minute ago, we'll end a little early so we can go over the project. Topics for today, I'm going to briefly talk about the main applications we're going to see for the rest of the semester. I'm really excited about the rest of the semester, actually, because we're going to get into applications really deeply. And those will be related to your project. Content-wise today, I want to talk more about local linearization. And then focus on using derivatives to understand functions in the graphs, emphasizing theorems as needed. And I'm going to put this in the context of an optimization problem as well. And many of the project possibilities are optimization problems. But what are our applications to come for the rest of the semester? A big area of application is families of functions. Functions of a similar kind of nature are often called families of functions, and this is going to continue to include more multivariable calculus as we continue thinking about those things. Optimization is a big area of application of derivatives in calculus. One, maximizing and minimizing functions. In real life, think about business situations, you might want to maximize your profit or minimize your expenses. Those are common kinds of applications. And so we'll get into a lot of depth about that. Many different kinds of applications there. Talk about exponential versus something called logistic growth. We've already talked about exponential growth before, but now I also want to talk about another kind of growth called logistic growth. It will include an introduction to differential equations, and then there will be some more applications of differential equations. Cooling and heating, something called Newton's law of cooling and heating. Free fall, but now we're going to add in air resistance. Harmonic oscillators, also known as masses on a spring. Maybe we'll get some friction in there as well. All these things you can see are related to differential equations, diffie-qs for short. Data modeling, that's important for statistics and data science, including machine learning and artificial intelligence, like the subject of that documentary I sent you information about, or a link to. Related rates, many different types of applications there. More on physics of motion. We'll get into 2- and 3-dimensional motion a little bit. Not in a ton of depth, but we'll try to get the basic idea about it. We'll still talk about distance, displacement, speed, velocity, and acceleration, but we'll also talk about vectors a little bit. Flow rate applications. That could be sort of, water flowing into a tank, for one thing. That would be a fluid flow. Can we find the accumulated flow? Meaning, can we find the total volume of the water as a function of time if we know the flow rate? If it's constant flow rate, that's easy. Just multiply the constant flow rate times the amount of time. But what if the flow rate changes? We want to know how to handle that kind of thing. And that is not just for fluids, but also for applications such as cash flow, money flowing into your bank account. Doesn't that sound nice? Money may not be flowing into your bank account every second of every day, but it is probably flowing into Amazon's bank accounts every second of every day, right? They're making so much money that you can effectively think of cash as flowing. And for cash flow, we might also consider discounted cash flow, which means essentially taking interest rates into account, okay? And thinking about present values. So that's a lot of applications. We've got a lot of content to do. We are about 2/3 of the way through the semester. My plan is the project is going to be due the second to last week. I'm not sure which date, maybe Thursday night again. And then our third exam is going to be Wednesday of the last week of class. It will not be cumulative. The next week is finals week. The final exam will be cumulative. Okay? So you will want to start, you will want to continue reviewing past stuff every once in a while as well. We formed the foundation. We've got a lot of factual knowledge under our belts, for example, including rules like the product rule and quotient rule and chain rule, and the local linearization formula. We want to now use those tools to do applications, like I mentioned here. Okay? And we're also going to introduce integration, and that will come up in applications as well. What about the theoretical stuff? What about the theorems, like the increasing function theorem and the decreasing function theorem and the constant function theorem, and there will be other theorems too. I will still talk about that, but on a as-needed basis, okay? I want the applications to be the main content that we focus on. And then as we need them, we'll talk about the theorems. So I would continue suggesting reading section 3.10 with all those theorems in it. We will use them, and you will want to know them, but we'll sort of discuss them in a more natural way in relation to the applications starting today. Okay, so today the star of the show is the applications. Before we get into some of those applications, I want to introduce you to one of my new favorite websites. It's called windy.com. And the reason I went to windy.com was because my daughter and her husband live out in California where there were all those wildfires recently. And they were actually pretty close to a fire, and the wind was howling. And we were worried about the fire getting toward their home. And so I found this website, windy.com, that gives you pictures that look like this. And it's a little hard to see. Maybe I'll try to go to the website here as well. But not only do you see a map, but you also see different colors that represent different wind speeds. The more purplish, reddish kinds of colors represent very high wind speeds. And the blue-green colors represent slower wind speeds. And if you look real close, or zoom in real close with the camera, you can see like little lines all over the place. They're actually little arrows. What we're looking at here is something called a vector field. And if you go to the website itself, it will actually play that for you. And those vectors move to animate the wind speed. So we can see what the wind is doing here in Minneapolis, St. Paul right now. It looks like it's mostly going from south to north. You can see those arrows moving. Zoom in if you need to. And yeah, bluish is a little slower than greenish. So it's a little less windy here in the Twin Cities than it is further away. Okay? So I was using this, and you can also predict the future with this too. It's a forecast. You can go into the future and see what the winds are going to be like. We're going to have any windy times here coming up. No, it doesn't look like it's going to be too windy in the near future. Okay? Why do I bring this up? Well, it is related to calculus. Flows. This is an example of a flow. You might say a fluid flow. The air that we breathe can be thought of as a fluid, even though you usually think of fluid as liquid. And calculus methods can be used to construct this kind of a picture and also to understand it. So that was something that I enjoyed, and I just wanted to alert you to that. All right, let's get into some applications now. Two main applications today. One application is more linear approximation. The second application is an optimization problem. What I'm going to show you here is a problem about estimating percent changes in a function. Okay, and this is pretty useful. You're going to have two homework problems related to this that are completion problems. One of which is even, so I think I might have to give you some hints on Moodle about that even problem, or over email later today. I might not have time until later this afternoon. Couple problems in that section related to linear approximation. They're pretty important. This is an important kind of application. As we've seen before, I'm going to go to a mass in a spring here. When friction is negligible, the period t of the mass in a spring, where the mass is m and the spring constant k, is given by this equation here. I'm purposely doing something new, just to emphasize the connection to multivariable calculus. I'm giving this function a name, f. Notice this is a function of two variables. Okay? This is going to be important for using Mathematica for your project in ways that I'll show you here today. Give that function a name. It's a function, again, of two variables. It's a multivariable calculus function. Before, I haven't always put that there. Now, I'm not going to refer to that function name in what you're going to see to come here, though I will use it in Mathematica. Okay? So what's the goal here? We want to answer some questions. Did you know that math is all about asking questions and trying to answer them? I mean, you asking questions, not me. You asking questions of the math that you're doing and trying to figure out answers. It's not just, I want to get done as fast as possible, just get the right answer and go on, though I understand that feeling. It is trying to understand by asking questions. So we can ask the question, what is the approximate change in t, the period? how long the mass takes to go back and forth one time. If the mass m itself changes by a certain small percent, maybe it grows by 2% because you're using like a bigger piece of wood or something for your mass in the spring. Second question would be, what is the approximate percent change in the period if k changes by a certain small percent? K is the spring constant. Bigger K's are like stiffer springs, they're stronger, they have a larger restoring force. Smaller K's are weaker springs like slinkies. Okay? To do this kind of problem, to answer these kinds of questions, does take some slick algebra that you'll see here. And I wouldn't expect you to be able to figure out the slick algebra unless I told you the answer ahead of time, and that's what happens in the book's problems. You know the answers ahead of time, and you want to figure out the slick algebra that's going to get you there. And it also needs to, we need to use local linearization, along with the fact that for a function y equals f of x, the relative or percent change in y, as x changes from some number, call it x, to x plus delta x. So I'm not using the infinitesimals here, though I could. Is the total change in y divided by the starting amount. If you think about examples, that can make good sense. Like if the initial amount of money in a bank account, let's call it y, is $10,000. And if the change, well, if the, let's call it a new amount. If the new amount in the bank account is the original amount plus the change in the amount, and let's say that's $10,500, that means the change in the amount is $500. It went up by $500. The ratio delta y, the change in the amount, divided by the original amount, $500 divided by $10,000, that's going to be 0.05 or 5%. It's a 5% relative change, okay? Percent change. In terms of function notation, that's f of x plus delta x minus f of x, all divided by f of x. This thing right here is the same as f of x plus delta x minus f of x, because f of x plus delta x is the 10,500, and the f of x is the 10,000. F of x is the starting amount, 10,005. F of x plus delta x is the ending amount. This difference is how much y changed, 500. That ratio then, again, represents the relative percent change in the amount of money. Okay? If you think about examples like that, it can help you give meaning to this symbolic form. All right, on to solving these questions. First, recall that formula from the previous slide. What should I do? Use local linearization. In terms of partial derivatives, you can write it like this. The change in t, the change in the period, is approximately the rate of change of period with respect to mass, partial derivative of t with respect to m, times the change in m. Again, I emphasize, I don't have to use partial derivative notation here. I could use ordinary derivative notation. It's okay, it's just notation. All this partial derivative notation is doing is emphasizing that the function depends on more than one variable. That's all it's doing. It's reminding you. Okay? This is distance equals rate times time. Not exactly, but by analogy. Instead of the total distance traveled, this is the total change in the period. Instead of the rate being a speed, this is the rate of change of period with respect to mass. If the mass changes, if the object gets bigger, how does that affect the period? And this is the, instead of the elapsed time, that's the change in the mass. Now, masses don't typically grow over time. Usually you're taking one mass and taking it off and then replacing it with another. But I can still think about the change in mass that way. What should we do with this now? Well, find the derivative. Differentiate this with respect to m. I'd have to bring the 1/2 down in front. The 2's would cancel. I'd have pi m to the negative 1/2 times k to the negative 1/2. And that, well, I'm going to write it in an unsimplified form. I'm purposely leaving the half here and not canceling with the 2 for a reason. What is that reason? I'm going to rearrange this like this. Why in the world would I do that? Well, for one thing, by doing that, and this is something that would be difficult to see without me telling you, this thing in the numerator is equal to t. Compare. 2 pi m to the 1/2, k to the negative 1/2, that's the same as the period. And so I can rewrite this change in t, change in the period, ultimately as this product, the original period divided by 2, times the relative change in the mass, the percent change in the mass. What's the usefulness of that? Divide both sides by t right now, and you get this equation, this approximate equation. And so now what this is saying, if you think about relative percent rate of change, that is the percent change in the period. That is the percent change in the mass. And we're saying for small percent changes in the mass, like 1 or 2 or 3 or 4 or 5%, the percent change in the period is going to be about half of that. That's a pretty profound thing, actually. Now, it would take experimentation to verify that. But the math says, assuming this formula is accurate for how the period of the motion depends on the mass and the spring constant, this is going to be true. The percent change in the period will be about half the percent change in the mass. We'll verify this with Mathematica here in a few minutes. We can also do this with the spring constant instead of the mass. If k changes, how much does the period change? Again, that's a linear approximation. The analog of distance equals rate times time. Find that derivative of the period with respect to the spring constant. There you go. And again, I purposely left it unsimplified and did not cancel the 2's because now I want to rewrite it like that. Just double check in your mind here that I did it correctly. Differentiating with respect to k, the negative 1/2 will come down. Subtract 1 from negative 1/2, I'll get negative 3/2 like you see here. So I purposely wrote it like this way, then I bring the negative sign out in front. I also decided to split k to the negative 3/2 into k to the negative 1/2 and k to the negative 1. Why? Because if I do so, look at this thing in the numerator again, it's the same as t. Once again, we get t in there, with a negative sign this time. And we can rearrange that, divide both sides by t, and get this approximate equation. Once again, we got the relative or percent change in the period approximately to some constant times the percent change in the independent variable, in this case the spring constant. In this case it was the mass. Again, something pretty profound. If the spring constant increases by, say, 2%, you should expect about a 1% decrease in the period. Does that make sense? If the mass changes by 4%, if it increases by 4%, the period is going to increase by half of that, about 2%. These are pretty profound approximations that you wouldn't necessarily expect unless you actually do the math. Let's test these approximations now out of Mathematica. You will want to try to pay more careful attention to the Mathematica I do in the last third of the semester because, again, with the project, you're going to be using Mathematica, not in a predefined way like with project number 1, but in your own way. So you're going to want to listen to how I tell you to use Mathematica. Okay, and for this problem, pay attention to details here. Here's how I would enter the function. Notice, as I have told you before, that when you define a function, you use square brackets for the input, not parentheses. Secondly, when you first define it, you need underscores after the variables. And I've got 2 independent variables here, an m and a k. I've got to use the underscores. That's essential when you are defining the function. Also tend to use a colon equals. That's actually not quite as essential. I could just use an equal sign. I, by force of habit, for some other reasons, tend to use a colon equals when I'm first defining the function. There's the formula. Once I enter the function, if I want to see that formula again, I can just type the function name without underscores. You only use the underscores when you're first defining the function. I can see what it looks like this. Okay, and Mathematica sometimes rewrites it in ways that you did not write. I wrote it with powers, it's writing it with roots. But it is the same thing. You can also plug in numbers. Two variables, I can plug in two numbers. I can plug in, for example, m is 4 and k is 9. And the period, always remember what this equals, this is the period, capital T, would be 4 pi over 3. A large period, that would be a very slow motion. If the mass is 4 kilograms and the spring constant is 9 newtons per meter is the technical units for it, that's a very slow oscillation. The period, 4 pi over 3, what would that be, like 4 seconds or something, somewhere in that ballpark. 1001, 1002, 1003, 1004. It's an oscillation about that fast is what it would represent. You can differentiate with respect to either m or k using this kind of syntax. Capital D means differentiate. If I want to differentiate with respect to m, I put a comma m here. If I want to differentiate with respect to k, I put a comma k there. Before, we've differentiated with primes instead of capital D. But you've got a function of two variables here. If I just use a prime, Mathematica wouldn't know which variable I'm differentiating with respect to. So it's good to use the capital D here. All right, let's confirm these relative changes. For example, if we change the mass by 2%, what is the approximate relative change in the period? It should be what? Based on what was on the other slide?
1%.
1%, half of 2%. Is it? Do this calculation. Notice this is the change in the period. The mass is, the initial mass is 100. The new mass is a bit bigger, 102 kilograms. That's so big you can't lift it, right? I did not change k. K is 5. That's the change in the period divided by the original period. It should be close to 1%. Yes, that's close to 0.01. 1%. And I purposely did a couple other ones because I'm trying to emphasize it doesn't really matter what k is, for example. Here k is 200 instead of 5. Here k is 500 instead of 5. And I'm also changing the mass. But each time I'm increasing it by 2%. And in fact, this function is special enough that every time you do that fraction, you get the exact same number. That doesn't always happen with these approximations. But with these square root related functions, it does happen. See the big point. If I increase the mass by 2%, the period is increasing by about 1%. And it works for other percentage changes, 4% and 10%, though the approximation is not quite as good when the change is bigger. So these numbers are all the same, close to 2%. Half of 4%. These numbers are all the same, close to 10%, or 5%, excuse me, half of 10%. But it's a little further away from 5% there than the other one was away from 1%. Approximation is not doing as well when the change in m is a bigger percentage. Same kind of things can happen with k. I can increase k by 2%. What's the approximate relative change in the period? It should be negative 1%. So all these numbers, where I'm increasing k by 2%, for example, from 5 to 5.1, or 200 to 204, those are 2% increases in k, 500 to 510. These are, give you about negative 1%. Yeah, these are all pretty close to negative 0.01. 1% decrease approximately. And I can increase k by different percentages as well. once again, the percentage change in the period is negative half of what the original change is, approximately. Okay, so you can always take these theoretical results and verify them and try to understand them with computations. I highly recommend doing that. Mostly just for your understanding, so you understand what's going on. Can I clarify anything there? Please stop me if you want something clarified. Again, these are tricky calculations, the ones I did here. That's pretty tricky. You know, knowing to do this and then to do that is a pretty tricky thing. And also realizing that this thing is the same as capital T is another tricky thing. So I'm teaching you about this. You've got, again, a couple homework problems that are similar to this. They tell you the answer ahead of time, at least in one of them. Again, maybe I'll need to tell you the answer ahead of time in the other one, because I think the other one's even, I think. But this is the kind of tricky algebra you should do. It'll take some scratch work to figure it out. All right, on to optimization. And again, continuing to use Mathematica for visualization. Not to for, but just for visualization. This is again going to help with project 2. All right, again, we'll hand those out at the end of class today. Different possibilities for project 2. Many of which are optimization problems. Not all of them, but many of them are optimization problems. Here's your typical kind of optimization problem. If a can of soup is to have a fixed volume V, and you can pick a particular number for V, what dimension should it have, height and radius say, to minimize its surface area? Get the idea here? We're thinking about soup cans of different possible dimensions, maybe tall and thin, like that, maybe short and wide, like a hockey puck, or probably something in between, more like an actual soup can that you would see. Pretend all these have the same volume. Even if they have all the same volume, they don't necessarily have the same surface area. I'd like to find which one of these has a minimum surface area because, well, that might be approximately equivalent to minimizing cost. Now, it's not exactly equivalent to that. And in fact, one of the project possibilities involves investigating not just the dimensions of a soup can, you can zoom in on this if you want, not the dimensions of the soup can necessarily is giving you a minimum surface area, but also taking into account welding costs and things like that. Okay? That's one of the what one of the projects is about, taking welding costs into account as well as the fact that maybe the size of the can and the top and the bottom of the can are made of different kinds of aluminum, for example, and have different costs per unit area. But to keep it simple, let's just focus on minimizing the surface area. This is often written in terms of what's called an objective function and a constraint. There's a class being taught right now called Operations Research. Patrice Conrath in our department is teaching that. They do something called linear programming, where they're always doing this kind of thing all the time. They're optimizing some function, like minimizing some function, or maximizing, subject to some constraint. What function do we want to minimize? It's the surface area. What's the formula for the surface area of a cylinder? If you don't remember it, you should be able to figure it out. At least if you remember the formula for the area of a circle. If the radius is r, the area of a circle, I hope you remember, is pi r squared. And if you take that and multiply times the height, that is going to give you the volume. But what about the surface area? The area of this circle is pi r squared. The area of the circle on the bottom is also pi r squared. What about the area of the sides? Imagine taking a scissors and cutting the side and unrolling it. What would it look like? A rectangle, yeah. Area of a rectangle is base times height. Height is h. What's the base? It would be the same as the circumference of the circle, which is 2 pi r. So the surface area is 2 pi r times h. That's the area of the side of the can. Then you've got 2 pi r squared for the area of the top and the bottom combined. 2 because there's two, one on top, one on the bottom. And that's the thing we want to minimize. That's a function of two variables. I'm going ahead and using function notation here, again, for the purposes of putting this into Mathematica if I want. That's the thing that we want to make as small as possible. Not just for any values of r and h, though. They're constrained. They're constrained by the fact that I've got a fixed volume. That this number, v, is some fixed constant. That, again, in many homework problems you'd be told a specific number. 500 or 1,000 or something. Maybe in cubic inches. I want to do this in a little bit more generality, because that's what you're going to need to do on the project to be able to get some extra credit, like I need to do that before class. I'm going to help you learn how to do this in more generality. What are we subject to? A constraint. The volume must be constant. The volume as a function of h and r is pi r squared h. That in general is a function that will give you different volumes for different heights and different radii. But I'm pretending I know that's a constant, c. Not specifying the constant at the moment. I want to have this flexibility of being able to consider what happens when I change the constant. Wait a minute, how can you change a constant? Well, again, remember, whether something's a constant or a variable is all in your head. So initially I'm thinking of it as a constant, but then later I might want to say what happens if I now treat it as a variable. That might tell me some useful things. How do you do this? What are the steps? Got a step-by-step process here for this kind of problem. The first step is to solve the constraint equation for one variable in terms of the other. The volume is the constraint equation you've read there. Say h in terms of r. That might be nicer, because if I tried to solve for r in terms of h, then square roots would become involved. And I think I'd like to avoid square roots if possible. So let's do this first step on the board over here. The volume is, again, g of RH is pi r squared times h, and I'm pretending that's a constant. Call that constant c. In a sense, I'm setting it equal to the constant. It's not always constant. Okay. As r and h vary, typically you get different numbers for the volume. But I'm setting that equal to a constant, and in that situation, I can solve for h as a function of r by dividing both sides by pi r squared. You can leave it like this. You could also write it like this if you prefer. Either way is okay. What kind of domain for this thing would have to be true? Well, radii can't be 0. They can't be negative. R would have to be positive. Actually, have a can't, right? R would have to be positive. And h would have to be positive as well. That's the first step. Step one. What's the second step? Plug this into the objective function to get s as a function of just r alone. Also depending on c, but pretend c is constant. What do you think I mean here? Plug this. What's this? This is this, or this. Plug it in for h. C over pi r squared gets plugged into the f function in place of h. And the f function is up here. So go ahead, where you see an h right there, replace it with c over pi r squared. So we get 2 pi r squared plus 2 pi r times h, but now replace h with c over pi r squared. And something nice happens, the pi's cancel. One of the r's cancels. And you can simplify this to 2 pi r squared plus 2c over r. Or for purposes of differentiation, if you prefer avoiding the quotient rule, 2 pi r squared plus 2c r to the negative 1. Now if c is a constant, which I'm pretending it is, that's a function of r. It's this function of r in terms of f. Should I give it a new name? You can. I think I want to give it some other name besides what I put in Mathematica initially. In Mathematica I initially put s, but I've already got an s there, so that might be confusing. I think I want to avoid s, r, c, and h. I don't want to use those letters. H would be the most natural next letter to use for a function name, since I've used f and g. But h already represents height, so that would be bad. Oh, why don't we go Greek? Let's call this phi of r. Phi, or phi if you prefer. Not forward from. Phi is what mathematicians tend to say. Phi is what physicists tend to say. I'm not sure about chemists and biologists. Maybe they don't really use it. Not sure about engineers. I say phi. Okay? I hope it doesn't bother you. I did ask a Greek prof. He said, well, either. You can use phi, you can use phi. Just like you can say data or data. Right? It doesn't matter. I say data because I used to watch Star Trek The Next Generation back in 1990 a lot. So I say data. One of the android on there is named data, not data. So that's why I'm used to it. What are we trying to do here? We're trying to minimize the surface area. We've got it written as a function of r when we know the volume's constant. A function of just a single variable. One variable calculus, not multivariable calculus. I could graph that as a function of r. Or, and hope that graph has a minimum, a low point. How should I find it? A low point's going to occur where the derivative is 0, the tangent is horizontal. So I should probably take the derivative of that and figure out where it's 0. Yeah, use derivatives to minimize s as a function of r. And check that you really do get a minimum value of x. Then use the constraint equation to find the corresponding value of h. Step 3. Find phi prime of r. C is a constant. Again, coming back over here, here's the equation. 2 pi r squared plus 2c r to the negative 1. Its derivative will be 4 pi r minus 2c r to the negative 2, right? C is a constant. Bring down the 2, just to get 4 pi r. Subtract 1 from the exponent. Minus 2c r to the negative 2. I just used linearity and the power rule. I brought this 2 down in front. 2 times 2 is 4. Subtract 1 from that exponent, you get a 1 there. Bring the negative 1 down in front, make that plus sign a minus sign. 2c r to the negative 2. I just said a minute ago, I want to figure out where this equals 0. Set this equal to 0 and solve for r. How? It's not a quadratic. It's a negative 2, not a positive 2 there. I could multiply everything by r squared. Get rid of the negative exponent at least, but I get an r cubed involved if I do. There's really no way to avoid the r cubed. You can also add 2cr to the negative 2 to both sides and rewrite this equation, say like this. Divide everything by 2. Yeah, multiply both sides by r squared. I divided everything by 2, and I also multiplied both sides by r squared. Divide both sides by 2 pi now. And finally, take the cube root. R would be the cube root of c over 2 pi. That is the value of r, where the derivative of phi is 0. It's called a critical point. As I continue working through this problem, I'm going to be introducing a lot of terminology from chapter 4, first couple sections. And I want to pay attention to it. Critical point, very important term, is a place either where the derivative is 0 or where the derivative is undefined. I guess you could say, well, it's got to be part of the domain. R equals 0 is not part of the domain. So even though the derivative is undefined at 0, the original function is not even defined at 0. You'd be dividing by 0. So since it's not part of the domain, you wouldn't call that a critical point. Critical points are points in the domain of the function where the derivative is either equal to 0 or undefined. Undefined derivatives could occur, for example, with the absolute value function where you've got a corner, or with the cube root function where you've got a vertical tangent. Those would be places where the function is defined but not differentiable. The derivative would not exist. Typically, they're mostly going to occur for us where the derivative equals 0. Now again, if I had a fixed c, I'm going to show you a graph with c equal to 500, in fact, 500 cubic inches, centimeters, excuse me. Then I'd have a particular number here. I could approximate with my calculator. But I want you to be able to handle it in general. Again, that's going to help you for the project. So this is something to work on, not just particular problems with particular numbers, but be able to handle general situations like this. I haven't done step 4 yet. Let's do that now. This is the radius, say, in centimeters. I didn't say it was centimeters, but I'm going to say it is in centimeters. What's the corresponding height of the soup can that is hopefully minimum volume? And I should also check that it's going to minimize the volume, or the surface area, excuse me. Over here. Step 4, plug that back into really this equation right here to solve for the corresponding height. Corresponding height h would be c over pi r squared, where r, I'm going to plug in that particular thing over there. See that again here? And this particular thing I'm going to plug in for r. It's the same as c over 2 pi to the 1/3 power. I'm going to square it, so I'm going to get 2/3 power. c over 2 pi to the 2/3 power, because I'm squaring the 1/3 power. And this can indeed be simplified a bit. This is the same as c over pi times c to the 2/3 divided by 2 to the 2/3 and pi to the 2/3. For the c, if you wanted the c to be on the top, you'd subtract the exponents. 1 minus 2/3 is 1/3. With the exponents of pi, down here you can subtract the exponents. 1 minus 2/3 is 1/3. And the 2 to the 2/3 in the bottom of this fraction can actually be brought up top like this. Because you can think of it as multiplying the top and the bottom of this big fraction by 2 to the 2/3. It's going to cancel on the bottom. And if you like, you can rewrite this as the cube root of 4c over pi. Right? Because 1/3 power is cube root. 2/3 power is a cube root squared. The 4 comes from 2 squared. Do we really get a minimum? I put that as part of part 3. Because you really can do that part of part 3 before part 4. Is it really a minimum? And not a maximum. We don't want to maximize the surface area. You can pick a particular value of c and graph it, but it would be good to know that it's the minimum for all values of c. There's a couple ways you can approach that. There's a first derivative test and a second derivative test. I'm going to do the second derivative test first. I'd like to verify that this point gives you a minimum surface area. Maybe the graph looks like this. And in fact, it will look like that. Kind of like a parabola, however, it's not a parabola. It's got a vertical asymptote here at r equals 0. Notice the graph is concave up, like a smile. To verify it's concave up, show the second derivative is what? How could I verify this is concave up? Yeah, the second derivative needs to be positive for that to be concave up. Is it? Find the second derivative and see. Find phi double prime of r. This is the graph of phi, by the way. Phi of r. I already found phi prime over here. Differentiate again to find phi double prime. Differentiate that, you get 4 pi. Differentiate this, we need to bring the -2 down in front, subtract 1 from the exponent. If you do so, you're going to get 4 pi plus 4 cr to the -3 power. Negative powers don't necessarily give you negative numbers, right? Because what they really mean, or what this one really means, is divide by r to the +3 power. And yeah, that's positive when r is positive. C is positive. So that tells me the graph of this function for all positive r is concave up, like a smile. And therefore, this has got to be a minimum point instead of a maximum point, a low point instead of a high point. This is, in essence, the second derivative test. I'm just describing it verbally and visually right now. I'm not writing it down. I did not write it on any slides for today. It's a verbal, intuitive description of something called the second derivative test. You should be reading about it. Maybe already read about it. page 189, section 4.1. So that would be enough to verify it's a minimum. There's another method. There's the first derivative test. I did the second derivative test first because it's a little easier, even though you have to take another derivative. The first derivative test is a little harder sometimes because you've got to think about the first derivative, and you have to think about, does it change sign from negative to positive as r increases through the critical point here? That number right there, by the way, is the critical point. That's r equals cube root of c over 2 pi. For a fixed value of c, that's where you are. And the second coordinate of this point is the minimum surface area. I haven't found that yet. I found the height of the candle. That minimizes the surface area, but I haven't found the actual minimum surface area yet. It would be whatever this number is. It would depend on c. Does the first derivative change sign from negative to positive? It's a little harder to think about. Especially with an example like this, I think. You have to think about what if r is less than this thing, or what if it's bigger than this thing? Again, that's difficult to think about here. What might be better is just to say to yourself, if r is really, really small, close to 0, that's close to 0, and this thing is actually far away from 0 because it's the same as 2c over r squared. I'd be dividing by a really small number if r is really small, making the fraction really big. If r is positive and close to 0, this is a small positive number minus a large positive number, the difference is going to be negative. On the other hand, if r is really big, like 1,000,000 or something, you got a really big number there minus a really small number there. It's going to be positive. So that's a quick verbal argument without writing things down for why the derivative changes sign from negative to positive here, and the first derivative test would say you've got a minimum in that case, which makes sense. The graph looks like this. The slope of the tangent is going from negative to positive. The sign of the derivative goes from negative to positive. You're going to have a low point. For maximum points, the second derivative would have to be negative, the graph would have to be concave down, and the first derivative would have to change sign from positive to negative. What is the minimum surface area? Let's end by looking at Mathematica. Oops, that's not Mathematica. Here it is. Here I'm entering my f and g functions. Sorry. Notice the underscores and the colon equals. Here I'm solving the constraint equation for h in terms of r. C over pi r squared. And back over here, that's this thing. That's how the height depends on the radius if the volume is c. I could plug that into the f function in place of h to get my phi function, which I called s here. I'll change this to phi. Hey, pretty. Where'd that come? I make a phi by doing escape ph escape phi. There's my phi function. Where does that match? That matches this, or this if you prefer. Now take its derivative and set it equal to 0. By the way, to get a subscript like this, And notice I am putting the c in the subscript to emphasize the function is a function of r, but I need the c in there as something that I can change. So I put it as a subscript with an underscore. As far as Mathematica is concerned, c is a variable then, but as far as taking derivatives go, you can use this palette over here in the subscript button, escape ph, escape c prime. Now you can go back to using primes. There's the derivative, and you can solve for where that equals 0. I can use a prime when I've got the c in a subscript like that. Where does this equal 0? What is the value of r? There's the critical points, including some complex ones. Which one do we want? We want this one. Let me copy and paste that. I can now find h by plugging into this expression. So let's copy and paste that expression. Here's the way you'd plug it in. You'd go slash dot. This is something a little weird. I can replace r by this thing. It's a way to plug something into an expression. And this is just a way to plug this thing in for r in here. Right? You wouldn't know that without telling you. There it is. There's the height for the minimum surface area. That matches, camera back over here, that matches this thing here in centimeters. Finally, what's the minimum height, or minimum surface area, excuse me. Plug in that, well, this radius into the phi function. There's the minimum surface area. You can write that down if you want, label it minimum surface area. It's kind of confusing with all the c's in there everywhere. We could plug particular things in for c, like 500. C is a volume. It would be in cubic centimeters. I can see the graph. This is the graph of phi. S is a function of r. Surface area is a function of the radius. It's got them in. At a radius, well, when c is 500 cubic centimeters, the radius for the minimum surface area is 4.3 centimeters, and the corresponding surface area is 348.7 centimeters. And we could also find h. I didn't do that. A certain number of centimeters. Okay? So this is our first example with optimization. I made it difficult because I want you to be able to handle these more difficult situations. In your problems, when you do optimization, from the book problems, you'll be typically having numbers, not arbitrary constants like c. But for the project's sake, I want you to be able to handle arbitrary constants. Now, we'll talk more about the project here after we're done with the lecture, but also in the days to come, beginning of the lecture.